Hi, and welcome to this short overview where we will cover one particular aspect of machine learning, which is the learning part. So, in a lot of the presentations, machine learning is merely a statement that we will learn the model, we will learn the machine things, and then we will use the outcome. Here, we will actually particularly look at the learning aspect and what does it mean to learn. In order for us to have a discussion, I've selected a use case which we call a binary counter, where we, from an input perspective, have the binary 000, which is a 0, 001, which is a 1, and then we want the machine to learn to count basically to the next number. So if we supply 3 zeros, we want the output to be 001. Also, we hear that this is different than regular programming. So let's look at one very simple example of how we could program this in a regular program using here just if then. So if we have the input 000, then we want the output to be 001. For this particular case, of course, this would probably be a simpler approach, but let's look at how we, from a machine learning, would actually learn a machine to do this. We will take one of the models that's available for machine learning, the neural network, and for that we have always an input. We have one or more hidden layers. Here we see two hidden layers, and then we have an output. We will also see for the neural network that every node, so the input, is connected to the next node and the next layer. And there's different designs, but for this design, we're basically connecting the input, all of the nodes of the hidden layer, similar to the next level. We're connecting this node to all of these, and similar in the end that the last hidden layer is connected to all of the output. If we do this for all the nodes, we will end up with a neural network looking like this, where we have connections between all the nodes. If we try to match that to the use case, we can take the input here. So on the left hand side, we see here that we have 110 as the input, and as we saw from before, we wanted to count one up, so we want the output to be 111. But now let's look at how we go from the left hand side to the right hand side, and in doing that we will narrow this down to looking at only the top flow. So for neural network, we have the input, which is 1. We always have the input multiplied by a weight. In the middle, we have an activation function, and the activation function is typically some kind of a mathematical expression. In this case, we will use what's called a sigmoid function, which basically takes the input, put it into this, and then produce an output from the activation function. This output again has a weight associated to it, which we'll multiply it with, and then we'll end up with the result in the output. If we take this step by step, then we'll say that the input, which is 1, will be multiplied by the weight. We will then use that as the x input into the sigmoid function, so this will be the calculation. So the output from this calculation will be put here, and then we have similarly a calculation where we take the activation value, we multiply that with W1, and then we will get an output. If we take a specific example, just to put some numbers in there, let's say we picked weight for weight 1 and weight 2, 0.5. We can see the math here is in the first step. We are multiplying 1 by 0.5, which is 0.5. As we said, we use that as the x in the activation function. And here we say activation function with the 0.5. It gives us a result of 0.3. Again, we use this output to do the calculation with the activation value times W2, which is 0.3 times 0.5. That gives us a value of 0.15. Of course, we know that the output we were looking for is a 1, and we actually came out with 0.15. So here we can say that the error we have is 0.885. This is how far we were off. Now, the only thing that is possible to adjust in this model here are the weights. So if we want to work on getting the calculated output to become 1, then we can look at what can we do with the weights. And of course, we could see that we got a lower value than we were looking for. So probably since we are multiplying with a weight, we should try a weight with a higher value. So if we try to make that value for weight 2 to be 1.5, we can do the same math. And here, so the last step now is that we are multiplying the 0.3 with 1.5, it gets 0.45, and now we have an error of 0.55. And if we quickly compare to before, so before we had the error to be 0.85, and now we are down to 5.5. And of course we can keep working on this until we are getting close to get the correct output. And all in all, basically what we're talking about here is then that the learning of the network, it actually means that we are finding the best possible values we can for the weights. So in this case, for the very simple scenario here, we will be looking at finding the right value for weight 1 and the right value for weight 2. Now, with only 2, of course, that's very easy, but if we go back to look at the bigger model we had, which would solve our entire problem, we will see that we will have a weight for every connection we have here. So in total, we'll end up with having 30 weights to work with. And of course, doing that manually is a big job and difficult job. And this is where we have math coming in. We won't talk about here, but we have some math algorithms, calculations we can apply to this to try to optimize these weights to make them best possible. One of the things that may be obvious as well is that if we move changing a weight, for example, here, then that will certainly also change the values down here, right? So it's not so we cannot just say we will optimate these weights without thinking about this one. So this whole thing have to be done in order for the model to come out with the right result. One observation is also that we keep using the word best, and if we go back to the example we had before, we have a calculated output at 0.45, and this is what we will see is that while we are looking for 1, what we will actually be getting is a number close to 1. We would probably not ever get the actual 1 here. So if we go back to the bigger model and we have solved this, for example, it is very likely that these are the kind of values we would see. Then we would see that for this 0, we will come out with a 0.012, 0.009, and then for the 1, 0.987. So basically what we're talking about is that we are getting close to the number, and then we need to do a final decision to say that based on these output, we think that the correct output here is 001, and that will be the result. But it is not the case that the output itself would actually be 001, and this is also why there is a process of a determination of what the output should be as part of this that will be needed. So if we go back to the model we have used here, where we have the input and we have the output, we said that we wanted to count, and this is what we were building the model to do. We said that we learn it to count by adjusting the weight and optimizing those. But if we look at the last part down here, and I don't know if you paid attention to that when I showed the slide the first time, but here we're basically saying that the next number after 7 is 0, which of course, if you know about counting, would be wrong. But I think this is also another key piece to the machine learning is that the model will learn what we teach it. So if we had actually used this as the input and said that the output should be 0, we would have told the machine to learn that, and therefore if it was given 111 and we have learned it, correctly learned it, what we've told it, it will come out with a result of 000. So it's also important to pay attention to what we actually learning the model to do, because it will do what we teach it, not it won't understand per se that it is now a binary counter. Thank you very much. And this was it for this topic. If you have other topics, please let me know, and I will try to have a look and see if I would be able to cover those. Thank you.